Student, in this video I am going to discuss about other few line clipping algorithms, and also along with that I would like to complete the whole clipping algorithm with few polygon clipping algorithm also. So start with Nicol line clipping algorithm. So actually in this algorithm it actually creates more testing regions around the clipping window. It tries to avoid multiple lines intersecting calculation. So initially what we have seen in Lian-Bursky algorithm, or in Sutherland-Hodgman algorithm, or we can say Cohen-Sutherland algorithm, they are try to check the intersection with various boundaries, with the four boundaries of the clipping window. So here what it will try to do in Nicol line clipping algorithm, they try to avoid multiple line intersections with four boundaries. There might be lots of intersections for a line, for any line that has to be clipped out using clipping window, and that is why in this algorithm they try to do avoid the multiple line intersection calculation. So initial testing to determine if a line segment is completely inside the clipping window can be done using previous methods. So initial testing, like to determine whether a line segment is completely inside or outside, that testing can be done with the previous method that has been used in Cohen-Sutherland algorithm or in Lian-Bursky algorithm, but they try to go for improvise that method. If trivial acceptance or rejection is not possible, then the NLN algorithm sets up additional regions. So if the trivial acceptance or rejection is not possible, then we'll go for Nicol line clipping algorithms. Here you can see, suppose the P naught is a point that has to be checked whether it is inside the clipping window or not. So here you can see three scenario where P naught can be inside the clipping boundary, or in outside here, or outside here. For line with endpoints P naught, there are three different positions to consider. All others can be derived from this by symmetry considerations. So any other observation can be derived from these three scenarios. For each case, we generate specialized test regions for endpoint P and which use simple tests like slope greater than, less than, like that, and tell us which edge to be clipped against. So here you can see case 1. So we are going to go through three cases, like these three cases, and any other scenario can be derived from these three cases. Find which of the four regions P and lies in. So P not here, and where the P and lies, we need to think about that. So find which of the four regions P and lies. So for this point P naught, this is one region, this is second region, this is third region, or this is fourth region. So here you can see this thing has been created by using that connection between P naught and the corner points of the boundary, and this part is called left, this part is called top, right, bottom. So find which of the four regions Pn lies in, means P naught, there might be another P dot which might be P end lies where. We need to calculate the line intersection with the corresponding boundary. If we can find that Pn in any other region, then we can find out the intersection here with that boundary. So that is the idea here in this case 1, where P naught is inside the clipping boundary, and case 2 is that where P naught might be here. Okay, so again we try to draw the these regions, try to draw these regions. For this, we'll try to connect with this point, we'll connect with this point, this point, and this point. So these are the corner points of the clipping boundary, and these regions will be named as like this: LT, LR, or LB. Obviously, any point stays in this region will be automatically outside the clipping window. That line segment will be automatically outside the clipping window. But any line is inside that clipping window, we can determine the intersection points. We can determine the intersection points if the lines goes through any region of this, like left bottom, left right, or left top, like that. So this is case 2, where we try to put the starting point P naught here and try to connect the P naught with the corner points of the clipping window. Find which of the four region P and lies in, then calculate the line intersection with the corresponding boundary. Case 3. In case 3 there is two possibilities. Here you can see suppose P naught connects with uh, P naught connects with this first. So here one line might not connect here. This is any line. This is any line in this region, or we can say midpoint. Okay, and this is connecting with this point, or you can say that P naught. We can say P naught is connecting with this point, this point, this point, and this point. And again here you can see this P naught is connecting with this point, this point, and this point, and this point. So here why two possibilities like that? Because this point and this point might be interchanged depending upon the position of the P naught, and that is why two possibilities. This connection of the corner points with the initial points P naught might be changed for different kind of scenario. So again, in this type of scenario also we need to find out where the Pn lies. It might be lies here, it might be lies here, here also, here also, here also, here. But if lies here, then obviously the point will be outside the clipping window, and the line will be outside the clipping window. Then we need not to clip the line if that line lies outside the clipping window or in that region. But if the line lies inside this region, then obviously we need to clip the line. So that is three cases we need to go forward, and in case 1 and 2 there is completely separated out, and in case 3 there is two possibilities. So here you can see how it will proceed. To determine in which region Pn lies, we compare the slope of Pn to P naught. So we need to find the slope of the Pn to P naught to the slope of the boundaries of the NL regions. So suppose the line N, Pn star points here. This is the Pn. This is the Pn. This is Pn, suppose. Then we need to find the slope of the line. And if we find the slope of the line, then we can find the intersection points with the boundary point, because we already know the boundary values of the clipping window. Then applying the boundary values with the intersecting line equation having the slope value, we can easily determine the boundary points. So that is the procedure. First, try to divide the whole thing in regions with respect to the position of P naught, and try to find the Pn where it lies, and then try to go for the intersection point, calculate the intersection point having the slope of the line, and then after finding the intersection point, you can easily draw out the line which has to be clipped using the clipping window. So number of cases explodes in 3D. So this is a 2D concept. If we go for 3D, suppose the clipping window is 3D, then number of cases might explode in 3D, making algorithm unsuitable. So this is a drawback in case of NLN line clipping algorithm. So next we are going to discuss about polygon clipping. Before this, I'd like to suggest you that please go through the textbook and also any other literature you can find over internet to understand the various line clipping algorithm like Cohen-Sutherland, Lian-Bursky, or an NLN line clipping algorithm. Try to do some problems with mathematics. Try to do some things which you can find in the book also. Examples you might find in the book also. So if you can do those things, then easily you can understand the procedure. But try to understand the basic concepts at first, so that you can deploy those concepts in the mathematics. Next, polygon clipping. Clipping a polygon fill area needs more than line clipping of the polygon edge, and would produce an unconnected set of lines. Here you can see, if we clip this polygon, it will create some unconnected line segments, and then we need to draw that region inside the clipping window, okay, with the specified color. So clipping a polygon fill area needs more than line clipping of the polygon edges, because it will produce an unconnected set of lines. These are the unconnected set of lines. Okay, must generate one or more closed polylines. So we need to generate one or more closed polylines which can be filled with the assigned color or pattern. Otherwise, if it become open, then we might end up with whole clipping window colored. So we need to follow a specific procedure to clip this type of polygon, so that we can find this closed polygon inside the clipping window also. Here you can see, find the vertices of the new polygon inside the window. So here this is the clipping window, outer boundary, this is the clipping window. Okay, this is the clipping window. We need to find which are the points inside the window. So in the Sutherland-Hodgman polygon clipping algorithm, they try to check each edge of the polygon against all window boundaries. So they try to check each edge of polygon, this one, this one, this one, this one, this one, and this one, against all clipping boundaries, and modify the vertices based on transition. And they will go for a transition, and according to the transition with the boundary and along with the edges of the polygon, what will Sutherland-Hodgman polygon clipping algorithm will do? They transfer the new edges to the next clipping boundary. So they try to transfer the whole polygon to a new boundary of the polygon, such a way that it is clipped against the clipping window. Here you can see, this is the original polygon. They try to clip the left part first. Okay, they will clip the left part of this original polygon. So they clip this part. Then again they try to clip the right part. Then again they try to clip the bottom part. Then again they try to clip the top part. So this is the process of Sutherland-Hodgman polygon clipping algorithm. Okay, processing a polygon fill area against successive clipping window boundaries. That is the procedure. Clipping window boundaries is left side, right side, bottom side, or top side. In that way, we will go through in this Sutherland-Hodgman polygon clipping algorithm. Here you can see how it goes through. Suppose you are traversing an edge for borders. 4 cases like P1 is going for P2. Then P1 is the P1 dash and P2 we need to keep. We can discard P1 to P1 dash part of the line. If P1 outside, if P2 inside, then take P1 dash to P2. If P1 inside and P2 inside, both are inside the boundary, we can take P1, P2 as a whole. And if P1 inside and P2 outside, then take P1 and P2 dash, this part only. And P1 outside, P2 outside, take none. So this is the scenario for any boundary. It might be top, it might be left, it might be right, it might be bottom. So you need to follow this procedure for any of the sides with respect to the edge of the polygon. Here you can see the procedure. Suppose we start with left border. Left border is this one. Here you can see for left border P1 and P2 both inside, because for the left border P1 and P2 both are inside. And again for any vertices. Same way, V2, V3 both are inside of this, edge. So any vertices for this polygon are inside this left border. So all the borders of the newly generated polygon will be the same as like before, because we have not found any vertices that is outside of the left border. Then we'll go for bottom border. Okay, we'll go for bottom border. So here you can see what it does. It will check like V1 and V2 both inside, V1 and V2 for bottom border. This is the bottom border. V1 and V2 both insides. Then we will take the V1 and V2. Then V2 and V3. V2 and V3 because that is a edge connecting in the polygon, and V3 is outside. Then we can say like that, V2 is I mean in, V3 is O means out. So V2 and V3 dash will take. V3 dash will take. So V3 become V3 dash, and V3 and V4 both are outside. We will not take anyone, and none will be taken. And V4 and V5 both are outside, then none will be taken. Again you can see V5, V6, V5, V6. V5 is outside, V6 IE, V6 is inside. So V5 dash is taken in place of V5. So new point of the polygon is become like V5 dash instead of V5. So here you can see V6 and V1 both inside, V6 and V1 both inside with respect to the bottom border. So V6 and V1. So new polygon points are V1, V2, V3 dash, because V3 is discarded, only V3 dash part has been taken. Then again V4, V5 is discarded, again V5 is taken, V5 dash is taken, and V6, and again completing the cycle of the polygon with V1. So new set of the polygon will be become like this. New set of the vertices of the polygon will be like this. Next we will apply the same procedure with the right border and top border. So right border, we are going to apply the right border operation on that set whichever resultant of the bottom border. So but the cycle of applying left, bottom, right, top might be different as per your choice, but whatever result come out in intermediate phases, you need to take those set of vertices in calculation process. So here you can see V1, V2, where V1 is inside, V2 is outside. For right border, V1 is inside, but V2 is outside. That is why V2 dash. And again for V2 and V3, V2 is outside and V3 is inside. Or you can say V3 dash, that is V3 dash. V3 dash is inside. So you take V3 double dash, V3, V2 double dash, V3 dash. And again V3 dash, V5 both inside, or you can say on the line, then it will considered as inside. So then again V5 dash, V6 both inside, V5 dash and V6, and V6 and V1 dash, V6 and V1, because V1 is outside, that is, so is, oh sorry, V6 and V1 both inside with respect to right border. That is why we need to take V6 and V1. But in the top order case, it will be changed to V1 dash. So with respect to each border, we are going to apply the same procedure. We'll try to shake out everything. So after we'll getting these points which are intersecting with the clipping boundary. So in that way, we'll find out this resultant set of vertices which will create the polygon after clipping. Okay, so that is the resultant polygon. So that is the process. So for every border, we'll try to find out which vertices inside or outside with respect to the border, and in that way we'll proceed, and everything goes through like clockwise or anti-clockwise as per your choice. But here you can see everything goes like clockwise from V1 to V2, V2 to V3, V3 to V5 dash, like that way. So try to go through like this to understand or to calculate or to find out the which part will be remained out after clipping. So this is the resultant clipped polygon. And again, here you can see same concept described here: out in, out in, out from, out to in, then output will be v1 dash to v2, in, both will be same, then in out, then v1 dash, then out out, both are out. Now none will be kept. The four possible outputs generated by left clipper depending on the position of a pair of endpoints relative to the left boundary of the clipping window. Next, the same algorithm, but there is a drawback in case of Sutherland-Hodgman algorithm. What happens is that the algorithm correctly clips convex polygon but may display extraneous lines for concave polygon. Here you can see in the original picture there is no line between this part, because this is a concave polygon, that is why there is no line. But after the resultant thing, you might see a line in the clip polygon part with respect to the clip window, and which should not be here, because this was not originally in the concave polygon, because you cannot understand, or this is a wrong picture with respect to this, and that is why Sutherland-Hodgman polygon clipping algorithm cannot eliminate this line, and that is the drawback of the Sutherland-Hodgman polygon clipping algorithm. So other issues in this type of polygon algorithm, like here you can see problem in Sutherland-Hodgman, and then Euler-Atherton has a solution. Clipping other shapes also, in suppose we need to clip other shapes also, then we might have problem. Clipping eclipse, circle, eclipse, curve. Suppose the clipping window is circle. Suppose the clipping window is this one. Okay. Then it will have some problem. Clipping the exteriors, you need to clip the exterior also, we might have some problems with respect to Sutherland-Hodgman algorithm. So next one is Euler-Atherton polygon clipping algorithm. So in this approach, another approach to polygon clipping, that is Euler-Atherton polygon clipping, no extra clipping outside the window, works for arbitrary shape. It can works for arbitrary shapes. Avoid degenerate polygons. We can avoid degenerated polygons if we apply Euler-Atherton polygon clipping algorithm. How it will apply? The outline is that replace the crossing points with vertices, form linked list of edges. We need to create a linked list of edges, change links at vertices, enumerate polygon patches. Now we'll go through this again, what this means. Here you can see this is the subject polygon, SP, and this is the clip polygon. So at any time, if we want to create this as a clipping polygon, or this as a subject polygon, then also this algorithm will work. And that is the benefit of this work. And also this is a concave type polygon, and how it works we'll see, because that does not work in case of Sutherland-Hodgman algorithm, because in that way Sutherland-Hodgman algorithm, in that algorithm it will create the extra line alongside this boundary, and which should not be there, as the main polygon does not have that type of line. But Euler-Atherton clipping algorithm will try to remove that type of problem. So here you can see in this picture you can see almost 13 edges are there. This is edges are there with respect to the clipping window. Here you can see 1, 2, 3, 4 and 5, 6, 7, 8, 9, and again 10, 11, 12, 13. Now again you can see here what it has been gone through. It's a clockwise direction. Here you can see 1, 2, 3, then we will start from this point, 4, 5, we will not leave these edges, 5, 6, okay, 6, then 7, then we are not going this side, we are going in this side, 8, 9, then again start from this 11, 12, 13. So you can see 1, 2, 3, then 4, 5, 6, 7, 8, 9, then again 10, 11, 12, 13, 14. In that way we will go through the lines of the or edge of the polygon. So here you can see 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, again clockwise same direction, 9, 10, 11, 12, 13, 14. So this is the procedure. So after the complete process, it will create this right answer. So start at the first vertex, that is a procedure. Clockwise orientation of polygon. Traverse the polygon until you hit a window. Here you can see until you hit a window. If you go through this, start from this point suppose and go through the clockwise direction, okay, and then until you hit a boundary, clipping boundary. If you hit a clip boundary, then try to find out the intersection point here. You have to find the intersection point here. Then again we have to turn right, then follow the window boundary until next intersection. So again here you can see 1 hit it here, 2 on the boundary itself, in the 3. So we have ended out. This is a complete cycle. Then again we need to start from this one because we have not gone through this part. This has been this, we need to keep that linked list, and we again start from 4, 5, 6. When we are going from inside to outside, then only we have to think about that turning right when we hit that, but not from outside to inside. So here 9 after coming inside. So again in that way. Output second intersection. Turn right again and follow subject polygon until close. Continue on subject polygon from first intersection point. Repeat process until complete. Can be extended to complex situations also. Arbitrary windows also. Stability issues can rise for such cases. So here you can see first point, that is 1. It will find out this. It will turn right. It will go through like this. 1 dash, 1 double dash, 1 triple dash, and complete here, and again resume from here. Okay, again resume from here, go like this, 2 dash to keeping track of the intersection with the boundary, then 3, 3, 4, 4 to dash, then again we'll going through this. We cannot go out of the window. A concave polygon defined with vertex 1, 2, 3, 4, 5, 6 is clipped using Weidler-Atherton algorithm to generate two polygons, 1, 1 dash, 1 double dash, 1 triple dash, and 4 dash, 5, 5 dash, 4 dash, 5, 5 dash completed. So that is the process of Weidler-Atherton polygon clipping. Counterclockwise orientation of subject polygon. We can do the same thing with counterclockwise also. We can go with the clockwise also, but orientation should be in a consistent manner throughout all the process, and that thing can be resumed and stopped. Here you can see after going through this at this point, that is stopped. Okay, after finding this thing, it will stop. 5, 6, stop. From an inside to outside pair of vertices, follow a polygon boundary. From an inside to outside pair of vertices, follow a polygon boundary. For an inside to outside pair of vertices, from inside to outside pair, for outside to inside, follow the polygon boundary. For an inside to outside pair of vertices, follow the window boundary. That is the most important point of this algorithm, because Other way you will get puzzled up in the process. So go with the polygon boundary in case of you are going outside to inside, in case of counterclockwise. For inside to outside pair of vertices, you need to follow the clipping window boundary. Polygon clipping using non-rectangular polygons. So in case of other type of clipping windows also, like here you can see this window is not a rectangular, so non-rectangular clipping window. So here we can apply same Wheeler-Atherton polygon algorithm. So this is why this provides a very robust technique to clip out the polygons with respect to any form of clipping window. So there is also text clipping. You can go through this. I am not going to give more focus on this part for time constraint. Try to go through this. You can find the book also, and if you have any doubt, please let me know. We'll try to resolve the doubts over Google Meet. Thank you.